right? Uh, keep on forgetting, right? Um, so we were at the point where we just finished calculating our mass, right? So our mass is 0.3. So are we seeing our screen? Are we seeing the screen? Yes, sir. No, sir. You can say I'm in the
Yes,
chat.
sir.
Yes, sir.
Yes, sir.
All right, good. So mass is 0.3. Right in here. So what do we put here? 0.3.
0.3 kg.
Right, 0.3 kg. So times what do we put as our G?
9.8.
All right, now we'll stop here. If our 9.8, if our G is stated in the question as 9.8, or if we are on another planet, right? Say we're on Mars or we are on Jupiter, and we carry the same experiment, G will be different. So you will see, and that it's not exact, but if a G is equal to 8, right, meters per second squared, right, or it could also be in newtons per kilogram. So you will see these popping up, these variances, but it's the same, essentially the same thing. Once G is equal to 8, we use 8. If G is on Earth, as you'll see in the next question, right, we're not going to do that question and leave that for another time, right? Because we're a little we're a little behind time, right? But if our G is stated as 8 or not, or say 12, right, we use the G that we get, all right, based on the question. So in this question, as somebody said, our G is 9.8. We are definitely on Earth for now, right? Now, somebody want to work this out in their calculators to get the final answer.
2.94.
2.94.
2.94, right? 2.94 apples. You remember the unit for force?
Newtons.
Right, newtons. All right, so somebody's reading over their notes. All right, 2.94. So, just remember this, guys. All right, I'll say this again, because I don't want to say that sir did not say this. I'm on a record. Right? If you see a different G, right? If we're on another planet, you'll find out that acceleration due to gravity or the force of gravity is different, right? Because of the size of the planet, right? So are we all understanding this here on the screen? Are we good? Everything here on the screen makes sense?
Yes, sir.
Yes,
Yes,
sir.
yes, sir.
And we essentially did the same thing in the class, right? The notes I posted on Google Classroom um have this working out, right? So please stop me, send a message in the chat, send a message to me privately. Um, before I move on, if I'm to go over anything, right? You don't have to tell the class. You can message me privately. All right. So we move on to the lesson today. I just wanted to clear this up because your test is on um Wednesday. I wanted to make sure that we are up to speed, right? All right, give me another second. Let me bring up this new topic. Right. So if we are calculating the if we are in grams, right, and are we are supposed to move it to kilograms, right? It is definitely 1,000. All right, guys. So 1,000 grams make up 1 kilogram. If you will see any other form of grams, I don't know. Well, you mostly see grams and kilograms, so it's mostly 1,000, right? If your question gives you in a ton, right, you have to learn how to calculate from ton to gram, ton to kilograms, and one ton is essentially 1,000 kilograms. So you can write that down quickly. I did a question on it in your notes. You can go back to that question. All right. So essentially 1,000 to move from grams to kilograms or tons to kilograms. Right. Um, bring this up. Make sure everything is good. All right. So, any other question before we move on to this new topic? Any other
No, sir.
questions? All right. So let's see how fast we can move. Right. Let me repeat again. You will not be getting this on this test. Right. You're not going to get it on this test. All right. This is a new topic. Let's see how far we can go. See how far we can go with this topic. All right. Uh, so let me know if you're seeing the screen. Yes, sir. No,
Yes,
sir.
sir.
All right.
Yes, sir.
So the topic essentially for today is conservation of linear momentum. Right. It's a big word, a big title. Right. But I will break it down as best as possible. Right. All right. So for this week, well, we'll move over to next week. But for this, in this, let me get my pen. We want to reach down to here, right? Apply the law of conservation of linear momentum. But before, we have some basic things that we need to cover first, right? And that's what we're going to do now. All right, so let's start out with a scalar and vector quantity. This is supposed to be vector, right? All right, so scalar quantity. So a scalar quantity only
Sir,
focuses question.
these notes will be on Google Classroom.
Right. These also be on Google Classroom as always, right? So you don't need to write. So a scalar quantity only focuses on size. You don't need to worry about this too much, right? Don't worry about this. Just know that a scalar quantity only focuses on the size, and vector quantity focuses on size and direction, right? So you don't need to worry about this. Just trust me. We're moving on. You will see this coming out more. So scalar, just a scale, just a size, while vectors we deal with direction and also the size, right? So scalar only focuses on, say, we're moving, or let's just say, vectors look something like this, where we have the direction, the arrow here pointing at the different directions, right? So just remember that. Um, we will see this coming out more, and if you have any questions we can always go back. But so distance, right? So I the distance is a scalar quantity, and what does that mean? It only focuses on size, right?
Yes, sir.
Right. So
Yes,
scalar
sir.
quantity, yeah, that describes the amount of space between 2 points. So we have a point A and point B. So the scalar quantity would be the amount of space between this guy and this guy right here, right? So it's the amount of ground, or it could also be described as the amount of ground covered by an object. So we have a person walking from here to here, right? This would be the distance of travel, right? So it's only size. While displacement, on the other hand, this is a vector quantity, and this means that it focuses on size and direction, right? So it's the amount of space between two objects in a direction, right? So if we are talking about displacement, if you ask what's the displacement traveled, we say something like he traveled 10 meters north, or he traveled 10 meters south, right? So we always include the direction when we're dealing with displacement rather than the distance, right? So it is the amount of ground covered by an object in a particular direction, right? The amount of ground covered by an object in a particular direction. So are we good so far? We have a better understanding, right?
Right.
Yeah.
Yes, sir. Right.
Yeah. So if you can send a message in the chat. Message me privately if you want me to go over anything. Right? Okay. So now we'll move on to speed and velocity. Right? The same drill. Speed is a scalar quantity, which means that it focuses only on size, right? And it describes how fast an object is moving. How fast an object is moving, right? While velocity is a vector quantity, which describes how fast an object is moving in a particular direction. So what do we mean by vector quantity again? What do we mean by that?
The size and direction.
Size and direction. Thank you so much. So we are having a better understanding, right? So how fast that object is moving in a particular direction. So we would say something like the velocity of that car is 10 meters per second north or 10 meters per second west, right? While for speed or average speed, the person traveled just 10 meters at 10 meters per second, right? And we'll see more of this coming out as we go along. So the distance, the velocity is essentially, as I said, the distance that an object moves per unit time, right? And we'll see this coming out, just trust me, right? We'll see this coming out, and we of course have in a particular direction. We must always have that when we're dealing with whenever we're dealing with vector quantities, right? All right, so as we said, the average speed, right, or velocity, right, is the same formula. We use the same formula to find it, right? But in different cases, we just have to ensure that we state whether it is in a particular direction, or we just need to know about the size, right? You won't find questions on this. This is just for information purposes. If I look over the past paper and I don't see them asking you what is the speed, well, what is the difference between speed and velocity. You will see one or two questions popping up, right? But you just once you understand the idea of scalar and vector, you should be fine as it relates to scalar and vector. And you see more scalar and vector quantities coming out, right? But we just need to cover that before we move on, right, into momentum. All right. So we have a formula here which represents the speed, the average speed, right? And we said that it says that the total distance covered, which is our S here, divided by time, the time taken to complete it. So bear with me. If Usain Bolt is running, say, 100 meters, this is 100 meters, right? 100 meters. Usain Bolt travels 100 meters, and he does that in I think 9.8 seconds. Is the record right? No, 9.58. Sorry, I am a horrible. Right?
Sir, you go divide 100 by 9.58.
Right. You're going to go ahead and you're going to divide 100 by 9.58 seconds to find out his velocity or his average speed. Right? So somebody want to try that? V equal.
Sir, it's 10.4.
Right. So he is moving at 10.4. Right. At the top we have meters. Right. The unit for S is meters. Right.
Right.
Yes, sir.
And the unit for time is what?
Seconds.
Right. So it is meters over seconds. Right.
Right.
And when we are using formula, we usually use the -1 or -2 to indicate that this particular quantity is in the the denominator, right? So we see something like ms-1. That is our unit for velocity. So because m, of course, is in the positive or in the numerator, and s is in our denominator, and it is at a power of 1, right? So our final velocity would be 10.4, and what is our unit again?
Meters.
Meters. What goes here?
S. Second.
-1.
-1.
Right.
Yeah.
So meters per second.
Second.
It means the per here is the fact that it's being divided. All right. Are we good so far?
Mm-hmm.
Yes, sir.
Yes.
Yes, sir. Yes, sir.
All
Yes,
right.
sir.
That's good.
Well,
All right. So we'll skip this for now. Acceleration. We will come back to this. Right. We'll come back to acceleration, but let's just move on for the last 4 minutes that we have. Let's just talk about Newton. Let's just introduce it. We'll go over it again, right, next week. Right, next week we'll go over it again. So, Newton's first law. Let's talk about this guy for a second. So, Newton's first law state that an object at rest will stay at rest, right, and an object in motion will stay in motion with a uniform velocity unless an external resultant force acts on it. And just bear with me, I'll try and explain this before any questions, right? So an object will stay at rest. So a if we have a fridge here, or let's just say we have a random box here, this box will remain at rest, right? Our box here will not move unless somebody, a strong person, right? A very strong
apply
person
force.
apply an external force, right? So somebody does apply an external force and it causes our box to move in. Let's just say the person applied the force F in this direction, right? So where would the box move?
In
Right?
the same direction it is.
Right. So the box will also move in this direction. Let's just say a car is moving, right? Not on a rough road, not like the roads in Jamaica. Let's say that it's moving on a very slippery road and it has no form of friction, right? I just wanted to get this before we go, right? Just understand this. So this is a car. Hopefully it comes out like a car, right? With a wheel here, right? Not the best car in the world.
Okay.
Yeah. So it's my car. Leave my car alone. Right. So we have a car going in this direction. It is on a slippery road, right? It's not troubling anybody, right? You know, like right? It's not being affected by friction or anything. It is just the road is not rough, it's very slippery. This car, trust me, this car will continue, right, until it will just continue moving and it will not stop, right? The only way it stops if it becomes rough or if there are any form of potholes which can cause friction. So the friction on the rough road, the friction, right? Which direction would the friction act in? If the car is moving in this direction, which direction would the friction act in?
So in the opposite
Opposite.
direction.
Right. So friction Fr would move in this direction while the car is moving. And as a result, what will happen to the velocity of the car?
So it will slow
Um.
down.
Right, right. Thank you so much. So the velocity of the car would decrease and the car would eventually slow down until it stops, right? Because of the friction.
Right.
But if there were no friction on the car and the road was very slippery, right? No form of friction, and the road was slippery. So we have some oil on the road, right? Let's just say we have some oil on the road. I know that's not possible, but let's just say the car is very slippery and it's not rough, right? You'll find that the car will continue moving until an external resultant force, such as our friction, begins to act on it and cause the car to eventually stop. Are we good? We understand?
Yes, sir.
All
Yeah,
right.
we're good.
All right.
Yes,
Thank
sir.
you.
Good.
Any questions you can just leave it in the chat. I believe that's the end of our class for today. Right?
Sir, it is.
I hear a question.
Sir, is it is hard? The physics test.
It depends if you study or you don't study, right? But it's not hard. It's not hard. It's I want to make this process as stress free as
Sir,
possible. For
does it have start answer?
no short answer, straight multiple choice 40. I'm still not at 40, but I'm working on getting 40 questions. All right. So any more questions before we go?
No, sir.
All right. Give me a second. So all right. So all the best, everyone. All right. You should have another class. All right.
All right, sir.
All right. All the best.
Sir.